So before I launch into the talk, I'd just like to say that this is joint work with Serge, Haziyev, and colleagues from SoftServe, as well as Yuanfang and colleagues from Drexel University. Okay, so here's my talk. Yeah, thank you. So to me, this is your typical software project, right? The boat is leaking, but you keep paddling. You are working really hard. And you're making some progress, right? You are moving the boat forward a little bit, but probably not very efficiently. And why are you doing this? Well, one is the illusion of progress. Yes, you are getting forward a little bit. And I would say, or ask another question, why don't you stop and patch the boat? Bail the water out of the boat? And I would say it's because of the lack of measurements. Your lack of progress, the technical debt, is less and less visible. And unless we do something, we're just going to keep working harder. We tighten our belt a little bit more. So technical debt has been a concept that we've been hearing a lot of. We've heard a lot about it at SATURN. But the state of the practice, if you actually look around at what people do to reason about technical debt, it's largely experience-based, intuition-based. People talk about code smells. It's still largely a metaphor. People say, yeah, I think this code base is getting ugly. And it's hard, it's hard to change. It's hard to understand. It's hard to modify. But software managers, right? Gregor Hoppe said this yesterday in his keynote talk. They're the money people. They make decisions based on dollars and cents. This is what Elcho was saying. And so you need to talk that language if you ever want to convince your managers, let's not deliver as many features this quarter, and let's pay back some of that technical debt. And your manager's going to go, are you nuts? Features, that's what we live for. That's what our customers pay us for. Technical debt, that's your problem, you whiny programmers. So how do we bridge this gap? So we're going to talk about a case study that we did in collaboration with SoftServe. And what we tried to do is to quantify the cost of the technical debt. How much was this slowing the boat down? How much was this impeding progress and impeding future productivity? And what would the benefits be of repairing the debt? And if we could quantify both of these things, then we could make reasoned business decisions based on something like return on investment, the same way other businesses make other investment decisions. And I'm hoping we can move software into this model that's more like other industries. Okay, so what did we do? We used this technique called the DR space, or design rule space, that I will explain. It's a clustering technique where we find important files in the architecture, and we find the other files that depend on those files. And these are the leading files. And they are design rules within your code base, and they lead a cluster of files. And we presented this idea at last year's International Conference on Software Engineering. And we visualized the flaws within these DR spaces, within these clusters, using a tool that we've developed called Titan. And then we extracted project data, data that was already there in their project repositories, in their revision control system, in their issue tracking system. We extracted data so that we could quantify the debt that these architectural flaws were actually incurring. We could say, you know, in these flawed areas of the architecture, you're getting more bugs, you're committing more code, you're making more changes, they're taking longer. And in these other parts of the architecture that don't have these flaws, look, life is actually better. So now we can start to make some cases about how bad it is and what the penalty is. And in doing so, we could estimate then the benefits of the refactoring. When you combine that penalty with an estimate from the architect about how much it would cost to refactor, to remove those flaws that we'd identified, you can make a cost-benefit argument and a business case, which you can then take to management. And management, if the business case is compelling, says, sure, I would be a fool not to invest in that when you put it in those terms. When I see that I could be delivering features much faster in the next quarter if I just spend a little bit of money to fix up some flaws this quarter. So what are architectural flaws? We've all seen them. We all know them. This is the big ball of mud, spaghetti code, tangled mess, interoperability problems, interface mismatch, mismatch assumptions, or just plain strange, inadvisable design decisions. Okay, so these are all metaphors, and I said I wasn't going to just talk about metaphors. So what are these actual design flaws? What is it that we find using Titan, our tool? Oh, and again, this is going to be presented in the upcoming WICSA next week in Montreal. Okay, so one kind of design flaw is cyclic class dependencies. A depends on B, depends on C, which depends on A, right? It becomes really difficult to modify A or B or C and really feel like you've got it right and you understand all those dependencies. And the cycles can be longer than just 3, but that's a simple example. And similarly, you find the same kind of cycles of dependencies among packages. Another thing that we see not infrequently is improper inheritance. So for example, I have class A, I have class B that inherits from A, and I have another class C that depends on both A and B. That's a no-no, according to object-oriented design principles. Or I have class A, I have B that inherits from A, but A depends on B. The parent depends on its child. That doesn't sound good. There are modularity violations. Let's say I have 2 different classes and they share some secret. Let's say they share some knowledge about a communication protocol, and that's hard-coded into both of those files. If you look in the project's revision history, what you will see is those files are consistently checked in together to fix a bug or to make a change, to add a feature, even though they have no structural dependency on each other, no structural relationship. This is a modularity violation, and we can find these by combining structural information with revision history. And if this modularity, right, that shared secret ought to be modularized, ought to be taken out and put in some third module that both of these modules then point to, and we only have to change one place in the future. And so if we can identify these and identify their economic impact, we might choose to fix those. And the 5th kind that we can automatically detect are called unstable interfaces. So that's where you have an important class, an important file that essentially acts as an interface. It's a class that other classes follow. So if you think about an abstract factory, there are classes that instantiate instances of factories. There are classes that implement the factory. There are classes that inherit from the factory. That factory interface leads a whole bunch of other files. And if that file, that leading file, is itself buggy and change-prone, frequently changing, it's going to cause ripple effects. All the files that depend on it are themselves going to be buggy and change-prone. And we've seen this over and over and over again. We've analyzed more than 100 open source and industrial projects. We can identify these flaws automatically, and that's the good news. This does not require human inspection. And in doing so, we can locate the actual cause, the root cause of the technical debt. We sometimes call these the buggy roots of the architecture. And combining this with project information about bugs and changes and commits, we can predict the economic impact of repair strategies. So let me give you an example. We represent architecture using design structure matrix. For those of you that are not familiar with this, it's just a square matrix. You list the names of the files as the rows. You list the same files in the same order as the columns. And the squares of the matrix you annotate with some information about the relationship between the file on the row and the file on the column. And of course, the diagonal is self-dependency. So in this case, this example comes from Apache Hadoop. And we're looking at the file system class, which is the leading file of a set of other files that inherit from Hadoop. So the primary relation that we're annotating in the design structure matrix is inheritance. That's what that IH means. File system is the leading class, and there are 7 child modules: filter file system, raw local file system, S3 file system, and so forth. Okay, so this makes a little DR space. Now we can add in additional information, an additional relationship between the files is dependency. And what we see from reverse engineering the code is that file system depends on number 6, distributed file system. And that sounds like a bad idea. So the parent depends on the child. How bad is it? Well, we can add in information looking at the revision history of the system, looking at the commits of the system. And so in each number in each one of those cells indicates a co-change relationship. So the number says file on the row and file on the column have been checked in together in response to some issue n times. So in particular, look at this guy. File system and its child distributed file system changed together 26 times in the revision history. Oops, hey, stop that. Okay. Furthermore, if you look at this lower triangle, these are all the co-change relationships between the children of file system, the child classes of file system, and they all change non-trivial numbers of times together, even though they have no structural dependency on each other. So this suggests that those children have some shared secrets that should have been but have not been refactored and moved up to the parent class. And therefore, they're changing together quite a lot when they should not be. That's kind of the point of inheritance, is to separate out the different stuff and put the common stuff together. Okay, so how do we get all this great information? How do we compute these DR spaces and the architecture flaws? This is our tool chain. The good thing is we do not require architectural documentation. We don't even have to interview the architect to get these insights. So that's why we're able to analyze open source software. We reverse engineer the code. And from the reverse engineering, we get a set of file dependencies. A inherits from B, A depends on B, A realizes B, A calls B. And we create a design structure matrix of all those dependencies, like that little example that I showed you. We also get the project's revision history, all of the commits, and we can represent that as a design structure matrix, just like I showed you. A and B change together. They change together 2 times, 3 times, 29 times. And finally, we get the issue list, the set of bugs and change requests. And if it's a good project, they have annotated every revision with an issue number, and so we can map between those. So we put all this information into Titan that finds builds the DR spaces and finds the architectural flaws for us. We export this information into spreadsheets, and now we have to talk to the architect. So we went and talked to Serge and his architecture team, and we said, here are the flaws that we found. Are these really flaws? Right? You've got a modularity violation here. You've got an inheritance problem there. You've got a cyclic dependency here. And they validated pretty much everything that we found. They said, yeah, we kind of knew that this area of the code was ugly and hard to maintain and hard to change, but we could never quite put our finger on what the problem was. So we pointed the finger, and we had the evidence to back it up. So they verified those architecture debts, and we then used information about how much penalty those debts were incurring in terms of increased numbers of bugs and changes and increased amount of churn, committed lines of code, so that we could quantify the penalty the debt was incurred and make then refactoring decisions. This is the Titan tool, and you can see this is a representation of a DSM, and we can select the kinds of dependencies that we want to visualize. We can zoom in on particular parts. So this allows us to have some flexibility in the kind of analysis that we do with the architect. Okay, so just to give you a bit of background before I tell you about the quantification, in our prior studies, we found a number of pretty interesting results by doing this clustering into DR spaces. First of all, if you have a leading class that's error-prone, it infects the rest of the files. So a DR space led by a buggy file is the other files are going to tend to be buggy. And in fact, the 5 largest DR spaces in the project capture more than half of the buggy files in the project. So this is good news. This means bugs are not uniformly sprinkled around the project, there are these clusters, locus of badness. And we can identify those, and we can also say what's wrong with them, and hence how to fix them. And if you don't do that, if you treat every bug as independent, it's like you're swatting out one bug at a time, but you're leaving the nest intact. And that nest is just going to produce more bugs because you haven't addressed the root cause. Error-prone DR spaces have structural problems, modularity violations, like the examples, the couple quick examples that I just showed you. And crucially, there's a strong correlation between the architectural flaws and the level of bugginess and change proneness. The more architectural flaws a file participates in, the more buggy it is, the more change prone it is, the more lines of code get committed. This is a very strong correlation. And so we're treating that correlation as a causation. I know you're always told not to do that, but we're going to do that. We're saying those flaws cause that increased level of bugginess. So, okay, based on an identification of these clusters, the DR spaces, and the architectural flaws within them, we can now go ahead and plan refactoring strategies. We can go to Serge and his architecture team and say, these are the clusters. And by the way, these are the problems in each of the clusters. Would you like to refactor those? And they say, well, mumble. Prove it to me. Prove that that refactoring is really going to pay me back. And that's the sensible response. It's got to make sense in terms of the economics. But the analysis is entirely doable based on available project data. We didn't have to ask them to collect any additional data. They just had to scrape what they had and give it to us. So let's take a look at the spreadsheet that we built. You can see it's not that big or complicated. So I'm going to zoom in on some parts of this spreadsheet. So first of all, we identified the three, in the case of their project, the three worst DR spaces. We renamed all of the offending files to be either a fruit or a vegetable. So they're led by pear.java, apple.java, and bean.java. And these are the sizes of the three DR spaces, 139, 158, 65 files in each of those. There were 797 files in this project. However, because a file can participate in multiple relationships with multiple other files, some of these files were actually in 2 or even 3 of these DR spaces. So to avoid double counting them, if a file participated in 2 DR spaces, we counted it as 0.5 here and 0.5 there. If it participated in 3, it was 0.33 in each place. So that's what gives us a normalized size, because we don't want to double count the penalty that a file is incurring. So these three DR spaces together represented 291 files out of the project total of 797. So it's a bit more than 30% of the project. If you look at the defects associated with the files in those three DR spaces, these are the raw numbers, these are the normalized numbers. There was about 240 defects in those 291 files out of a project total of 265. So those are 30% of the project, but about 3/4, 80% of the defects in the project. We also looked at the number of changes in the last year that accrued to those files, and there was about 1,500 changes out of a project total of 2,300. So 30% of the files, 80% of the bugs, about 2/3 of the changes, resulting in about almost 75,000 lines of code being committed out of a project total of 135,000. So more than half of the effort of the project went into these 30% of the files. At the same time, we calculated base rates for the project. So how buggy is the average file in the project? Well, there were 265 bugs and 797. Mine just died. Okay. 797 files in the project. So the average file incurred 0.33 bugs over the past year. Just divide 265 by 797. Similarly, the average file had 2.9 changes. That's 2332 over 797, requiring 170 lines of code to fix the bugs and make the changes. We also asked SoftServe for their corporate productivity numbers, and they said it's around 600 lines of code per person month. So that gives us a way of associating a dollar value with these lines of code that need to be committed. We then asked the architect, how much will it cost to do this refactoring? We told them which files were involved and what the problems were, and the architect could then make fairly confident estimates saying, yeah, to remodularize that set of files, to fix that inheritance hierarchy, to break that cyclic dependency, this is what it would cost. And so he estimated a total of 14 person months for the refactoring of those 3 DR spaces. Then we said, well, if you do the refactoring, and if we believe that correlation is causation, that by having larger numbers of flaws is the cause of higher numbers of bugs and changes, and so by removing those, we should return this section of the project down to project norms, then we would expect in the refactored version of those code, those DR spaces to have 39, 44, and 12 bugs in the upcoming year if they were refactored. And so that would be 96 bugs, resulting in a savings of 142 compared to how many they did have. We did the same thing with changes and lines of code. So look at lines of code. We said if these were refactored and they went down to project norms, there would be about 24,800 lines of code that they would not have to write. Well, divide by the corporate productivity numbers, you're going to save 41 person months of effort. So that's about a 300% return on investment in the first year alone. Okay, you don't believe my numbers. You argue with my assumptions. Let's say I'm off by an order of magnitude. That would be really bad. It's still 30% return on investment in the first year alone. Where can you get 30% on your money? Does GE get 30% on its? I don't think so. Okay, before 2008. So they're now doing the refactoring. In fact, the refactoring is supposed to be finished this month. And we are going to collect data, and hopefully in next year's SATURN we can report on how good those estimates were, and again, from collected project data, how many bugs, changes, and lines of code they actually experienced. So we're certainly going to continue this and validate the expectations. Okay, so the takeaways: architectural flaws lead to quality issues. There's a strong, consistent correlation that we see project over project over project. These things do not vary, at least over the, as I say, 120 or so projects we've now analyzed. And the good news is we can locate the flaws. We can do it automatically. This does not require a human to pore over code or UML diagrams or anything like that. And our contention is that we cannot fix the quality problems without fixing their underlying flaws, without fixing the root causes. So what this means is that by collecting this data, we can make informed, economics-based decisions about where, how, and if to refactor. This goes from a metaphor, a hunch, bad smells, to decisions based on empirical project data and sound financial reasoning. So with that, thanks for your attention, and I'm happy to take questions.
So when you're translating the data from Titan into economic decision-based data, and you say this is projected savings, do you take into account, you went right from it's going to take X amount of person months to fix this, and it's going to go right down to project norms for your defect rates. We all know code doesn't work that way in practice. Do you take into effect, or take into account in that transition that in reality you're going to have a higher code spike at first because it's a new refactored class, and then eventually you'll hit down to project norms?
No. So we haven't done that level of sophistication. However, in defense of us not doing that, I'd like to point out that project norms include these bad areas. So in point of fact, it might actually become much better than project norms because we think norms are already an inflated value. But again, this is an empirical question, and certainly once we get the data from their post-refactoring, we can look at that trend.
Have you looked at teams that you recommend the changes where they didn't have enough regression tests, which means touching any piece of code could turn into a nightmare? So it's not one-to-one.
Right, so the question was, have we looked at teams where they don't have enough regression tests, and so they don't understand the consequences of change? So maybe, Serge, you can answer that, at least for your case.
So the case is about legacy system, and it came to our company from another vendor. And regarding regression testing, so actually regression testing was in place. But the changes in this project required to switch from also old legacy technology like struts to Spring MVC as well. So that's why it was like a continuous change and continuous refactoring. And with Rig Titan tool, we could understand additional problems of it, and these additional problems didn't have much attention from our side. And now we understand that they slow down development. They slow down actually a new feature releases.
So, and just to add to that answer, part of what you're asking is, do we understand the dependencies between the code, and are we secure about making a change in the absence of a strong regression test suite? And I would answer that, of course, the regression test suite is the most important, but our analysis does give us insight about the dependencies, and this is insight that most architects lack currently. It's not visible. So
I was just talking about the math. When you do the math,
I see what you're saying.
If you don't have that, then you have to include, well, if I need to touch this code, I need to put enough tests around it, then I can touch it. So do you have that math?
Yes, okay, so that would be an additional cost.
However, there's an additional savings. I was only estimating the savings based on the lines of code you would not have to write, but there would also be QA costs that would eventually go down, and that would be an additional saving to the project.
And so is the Titan tool something you're sharing, or what are you doing with the tool itself?
Well, actually it's Drexel's tool, and they do make it available, but I can put you in touch with them to negotiate that.
Do it support other languages than Java?
Yes, so I didn't point it out, but we're using understand for reverse engineering the code base, and understand covers virtually every major programming language, C and C++ and C# and PHP and so forth. And we have integrated other reverse engineering tools as well, but we like understand. Yes.
Would you be able to tell changes to like configuration files and things like that that potentially we're trying to put, like data changes that are part of configuration? Would you be able to tell that?
Yeah, so the question was, could we track changes to configuration files? We've talked about doing that, but we haven't done it yet. But this approach is amenable to basically analyzing any kinds of dependencies. So another thing we've talked about but haven't done yet is runtime dependencies, things that you can't get from reverse engineering the code. So the answer is no, we haven't done it, but there's no principled reason why we couldn't. Okay, I think everyone needs to get to lunch, so thanks for your attention.